Hello there guys, and welcome back to another epic inexorable maths video. In this video we're taking a look at why it is that the derivative of the natural log of x is equal to the reciprocal of x, 1 over x. Why is this true? Because you might know that this is true, if you differentiate ln x, you get 1 over x. You might know that's true, but it's not immediately clear why it's true, right? Again, in previous videos recently, we've been looking at sort of differentiating funny functions like the modulus function of x, arc sine of x, and in the future we'll look at even more. And we employ different techniques in order to differentiate these things. So the issue with differentiating the natural log of x is, I would say, the same issue with trying to differentiate something like arc sine x. Where do you even start? How do I do it? I don't know how to do it. So here's the plan of attack. This is how you do it. You need to turn this problem into something that you do know how to do. And I mean, believe it or not, that will help you solve it. So let's actually put some numbers down, or some, not numbers, but just some maths. So we're trying to find the derivative of the natural log of x. That means that y is equal to the natural log of x, right? And we want dy dx. That's the whole idea. If y is equal to the natural log of x, dy dx. Again, we can't just do dy dx, right? Because that would be video done and we'd know how to do it. You might be tempted to say, oh, dy dx, it's 1 over x. But it's like, oh yeah, true, that's a fact, but wait, how do you actually get to that point? So, very similar to how you might differentiate arc sine if you've seen that video. If you haven't, it's no worries. What you can do is you can perform the inverse function on both sides. So we know that, for instance, the inverse function of arc sine is sine. And vice versa. The inverse function of applying the natural log of x to something is to have e to the power of that thing. Okay, so for example, we can say that if we perform the inverse function on both sides of these things, what we'll get is we'll have e to the power of both sides. So we'll have e to the power of y equals e to the power of the natural log of x, okay? This is a totally mathematically sound step because the base is the same. E and E. If the base is the same, then you can just look at the, this is like some GCSE stuff. You can look at the sort of exponential part of the equation and you can equate those things as well. So from this step, e to the y equals e to the ln x, you can deduce that y equals ln x. So you're kind of just going backwards from that and you're saying, oh, if they're both raised to the same thing, then it's fine. So for example, again, just to prove to you that this is valid, if I was to give you the problem like 2 to the x equals 2 to the 4, you might be like, oh, let me just take logarithms and so just look, they have the same base. So x is clearly equal to 4, right? Like you don't need to take logarithm. You just look at the exponents and notice the bases are the same. So you can just say x equals 4. So we're kind of undoing that. We're undoing it and we're saying e, which is a number, it's 2.7 and so on, to the y equals e to the ln x. Okay, I hope that step makes sense. Now, what we can then do is we can notice that we can say e to the y, that's fine. That we can't do anything with that yet. That's equal to e to the power of the natural log of x. Natural log of x is the log of base e of x. E to the ln x, here's an identity. E to the power of ln x is equal to x because they are inverse functions. So e to ln x is x, always. Okay, brilliant. Now, again, it's like we know how to differentiate both sides of this now. We know how to differentiate e to the power ofs, and we know how to differentiate x. So, we can differentiate both sides. There's one little catch though, we need to make sure we're using implicit differentiation. The reason why we need to do implicit differentiation is because we have e to the power of y on the left there, not e to the x. Again, how do you do implicit differentiation? Same as always, you simply pretend that the y is an x and differentiate like normal, and then times each term that has the y in it by dy dx. And again, this comes from the chain rule. So the derivative of e to the y with respect to y is the derivative of e to the y, so e to the y, times dy dx. Okay? We need to do the same thing to both sides. We need to also differentiate the right-hand side. What's the derivative of x with respect to x? It's just 1. derivative of x is just 1. Brilliant. And now what we can do is we can make dy dx the subject. That's the whole point, right? We want dy dx. This is equal to 1 over e to the y. Again, you might be tempted to say, okay, I'm finished, I'm done, everything is nice and I'm happy, it's finished. But look, the right-hand side is given in terms of y. We don't want it to be given in terms of y. We want it to be given in terms of x. We want dy dx equals some function of x, right? That's the notation that we like to use. It's way cleaner that way. It's much better. So we're not really happy with 1 over e to the y. We don't want that. We want dy dx equals a function of x. But this isn't a problem. Because again, how have we defined e to the y? Remember, we said that e to the y is equal to x. We deduced that earlier, which means that you are totally fine with replacing that e to the y with an x. And therefore, you get dy dx is equal to 1 over, not e to the y, but because e to the y is equal to x, it's 1 over x. So the derivative of the natural log of x is 1 over x. And that's everything that you need to know. Thank you guys so much for watching. Highly appreciate it. And I'll see you in the next video. Cheers.